Alright, hi everyone, welcome to my YouTube channel City of Electrons, and in this video we are going to do or study another method or another technique of numerical solutions. Okay, so in the last video we did Taylor series, and in this video we are going to work on a last method. Okay, don't worry, we'll come to PyCat. Okay, but let's take a last method first. Now this method can be seen as Taylor series, but with the truncation of derivatives higher than the first derivative. What does that mean? I'm going to explain what that means and show you how it looks like in mathematical expression. But first, bear this in mind. If we have a differential equation, let's say if we have this as a differential equation, saying dy dx, I should make this smaller. If we have this, sorry for that. Okay, let's say we have this dy dx equals f of x and also y. Okay, so if we have this, of course, let's just say, let's add the solution for y from this be 5x. Okay, so we say let the solution for y be this. Okay, so we are taking this as a solution for y. We don't know the solution, but of course we'll have a solution, and y will equal something, so let that something be this something. Okay, so now bear in mind that the points in the curve, and when we say curve here, let me just write that out. The points in the curve will be x 0, y 0, then x 1, y 1, and so on until we have x n, y n, y n. yn. Okay, so when I say points in the curve, this is what I am talking about. Let's say if we have this, and in this, or having this, and we have this. Okay, so this is of course f of x, or let me say that's y. Okay, of course y is a function of x, but let's just call that y and call this x. So this thing x0, y0, x1, y1, they are all points. They are different points in the curve. Okay, there are different points in the curve. Okay, this is not that perfect, but I hope you get the point. So this will be, so let's say this x0, y0, this x1, y1, x2, y2, just like that until xn, yn. So let me run through this x1 here. Let's say this is x1, this is x2, and so on until xn. Something to note. So I hope this can quite relate to this. So while this is x1, this will be y1. While this is x2, this will be y2. So they are just points, different points. So this point is referred to as x1, y1. They are just points in the curve. Okay, they are just points in the curve. That's what you have to bear in mind. Then this one thing to note is that these points from x1 to x2, they are equally spaced. That is, the interval from x1 to x2 is the same as the interval from x2 to x3, and so on until xn. But the thing is this, being that we have x, let's say this is a particular term. This can be x1, this can be x2, this can be x3. So if this is xn, what is the next term? The next thing after xn will be what? Xn plus 1, obviously. So if you add 1, you get the next thing. Okay, so we are trying to say that interval, the difference between this and this, the difference, that is x2 xn plus 1 minus xn, this difference is the h, which is the interval or step size. Okay, so you also just have this in mind, also very important. All right, well, let me go put this in brackets because we are going to need it later. Okay, good. Now, with that being said, we've written out that the solution be this. Okay, so if we now say, okay, we need the next term for y. Of course, this is what we have for y. Then the next term for y will simply be this n plus 1. I hope that's clear enough. Okay, will just be that. And we've said that the step size h equals this. That means we can, from this point, we can say that xn plus 1 equals h plus xn. We can say this just by move this guy to this other side. Okay, so we can simply say, we can say that. Okay, we can say that. That means everything here equals x file. Oh, I'm going to write you file. Let me put this in brackets and file xn plus h. This is the same thing here. I just turn the sides. Okay. All right. Now, with this being said, now I can do this. Let's go back to the definition. Okay. Now this point, I hope we all understand this point, what I just explained here. We are going to make use of it subsequent time. Okay, but just bear it in mind. Now, from the definition of Euler's method, or what we said about Euler's method, is that it is, or it can be seen as Taylor series, but with truncation of derivatives higher than the first derivative. So if we come back to Taylor series, this is our Taylor series here. Okay, so we copy the Taylor series. Like from the definition, it says it's just the Taylor series, but we truncate derivatives higher than the first derivative. So if we have our Taylor series here, let me put this from Taylor series, So from Taylor series, we will have this. We'll have this. Now, truncation of higher derivatives. Just take the higher derivatives like this and truncate. That's delete or cancel out, or we do not consider them, because if we go higher in the derivatives, the higher powers of h will give us, will be very, very small. So we ignore them. But ignore them in Euler's method. But since we ignore them in Euler's method, it will just increase the error. Okay, so it will not be that accurate in terms of approximation. Okay, so now this is just from Taylor series. That means we can say that the next value of y, which is yn plus 1, let me write that here. So yn plus 1, that's the next value of y, equals, now looking at this y0 is what we even see as the previous value of y, or let me just put this thing which we have said already as a solution. Remember, we said let this be the solution of y. Okay, so plus this thing we have here, x minus x0, this is the present x term minus the previous x term. Now that simply matches with what we have here. H is the present x term minus the previous x term. So you see why we have to bear this in mind. Okay, so that means in place of this we can just write h. In place of this, h. Good. In place of this we just put h. Then in place of this is first derivative of y. Okay, and we said this is the solution for y, so that's what we have here. Then this being the first derivative, go back to this guy, first derivative. Of course, y prime is first derivative, so first derivative is f of y of x. So it's just like saying this is y, then this y prime. So we can just put it this way, say, oh boy, this is large. So we can just say this. I hope you guys understand what I'm just written. That's fine. I don't mind the handwriting. So prime x n. Okay. If you want to put this in brackets, you can do that. Make it beautiful, beautiful. Good. So solution for y, which means this is solution for dy dx. This is dy dx, which is the same thing as y, which is the same thing as y prime. But we now say we are taking this one as a solution. Okay, so dy dx is the same as this, the same as y prime, and the same as this. So that's what we have here. Okay, y prime, that's what we have here. And then this represents y, which means the solution for dy dx is y, which is this. Okay, so, and it is obvious, yn plus 1, that looks like h, yn plus 1, that this is yn, can leave it this way, plus our step size, and this thing here is what we have as f of x comma y. So we can even just bring it this way and say this is what we have here. Perfect. This, my friends, is the Euler's formula. Okay, that's it, the Euler's formula. But we have to add this n. Okay, I think that should be clear enough. Let me try and make that clear enough. Okay, so that every eyes can see better. Okay, so this is the Euler's formula. Now let's solve a problem with it, so that or in our next video we'll solve a problem with it, so that we can see how this really fits in, how the Euler's formula fits in. Okay, or we can use it to solve differential equations. Alright, so this will be all for this video, and I hope this helps in one way or the other. Okay, so in the next video we'll continue from this part, just working an example with it. So thanks a lot for watching, and then bye for now. See you in the next video.